So hi guys, today we have another problem that is number of good components. Basically what they states that you are given a graph like this and you have to find or count all the fully connected components. Basically the good components means you have to count all the fully connected components. Like for this graph, this is a fully connected components. Why? Because we can go to one node to every other node by using one iteration. Means we can directly go to every other node. Like for 4, we can directly go to 5. But here, if you can see that for 1, we cannot directly go to 7. So this is not a fully connected component. And 6 is alone. So obviously this also satisfies in here. So the answer will be 2. Look, so the answer will be 2. Let us take another example. Let us open the Excel draw. Okay, fine. So let us take another example for this. Is it a fully connected component? Obviously not, because we cannot go directly from 1 to 4, because there is no path. So to make this component fully connected, we can introduce these edges, right? So then it will be converted into fully connected components. So how can we count all the fully connected components in here? So basically, we can use DFS and we know how to calculate all the connected components, right? So let us take this image here. So how can we uh, calculate all the connected components? That is, we can use a for loop like that. Okay, let us take some space. Where is the rubber? Okay, fine. Just take the pen. Now we can use a outer for loop that will be starting for 1 because the node is starting for 1 and it will go up to v, and there will be a visited array. 1, 2, 3, 4, 5, 6, 7. So we can call DFS for 1, then it will be checked here, then here, then here, and we will also visit 1, 2, and 7. So the for counter will be now at it at 2. So 2 is already visited, so we cannot call DFS again. Now for 3, we can call the DFS, and here also we have to count the answer because for 1 we can call the DFS, so that is 1, and for 2 we cannot call any DFS, and for 3 we can because 3 is not visited. So 3 will be visited as well as 4 and 5. So another component is found here. So now for 4 it is already visited, 5 it is already visited, and 6 it is not visited. So we will call DFS here and check it, visited it, and we got another answer, and that is 3. So basically this is how we can count all the connected components, but we need to count all the fully connected components, right? So we can modify this approach a little bit. How? Let us take another example. Suppose the node is or the graph is like this, and this is a fully connected components. And observe one thing for each node. How many out degrees are there? That is 3, and here that is also 3, and here that is 3, and for 2 that is also 3. So if it is a fully connected component, then always the out degree will be the total number of nodes minus 1. Why? Because if there is not a self loop, then obviously you can go to every other node except this node. So for every node, there will be the out degree of v minus 1. And how many nodes are there? That is v. And all the sum of the out degree will be edges here. And why I am taking edge? Let us see that thing. So in question, they are giving us the graph like this. If the graph is 2, 3, so they are providing the information like in this format. For 1, there is a connection, so that is 2, and for 1, that is a connection, that is 3, and also for 2, that is a connection, that is 3. So somehow we have to convert this information into this. For 1, that is 2 and 3. For 2, that is 1 and 3. And for 3, it is 1 and 2. And now we can say that for 1, there is an edge to 2 and 3. So how many edges are there? That is 2. For 2, there is 2 edges, that is 1 and 3. And for 3, there is one connection between 1 and another connection between 2. That is 2. Basically, we are converting this undirected graph to like this. And that will help us a lot. Now, for this node, for these connected components, how many out degrees are there? For each node, that is 2. And how many nodes are there? That is 3. So total out degree will be 6. And now sum all the edges of the this connected component, that will be also 6. So we can say that if we somehow convert this information into this, then the out degree and the edges both are same, right? So we have to uh, perform this operation, and then we have to modify the DFS. How can we? Basically, we have to count all the nodes in the component and as well as the adjacent nodes. Means when we are visiting one, then we will count one for this node and we will count all the adjacent nodes. And how we can find the adjacent nodes? The size of the current position graph, that is 3. So if this is the count of nodes and this is the count of out degree or edges, that is here, that is 1 and 3, that is also 1 for 3, and that is 1 for 3, and that is here also same. So let us sum this up. We will get 4 and we will get 12, and we can use this formula. So 4 into 4 minus 1, and that is 4 into 3, that is 12. So whenever this condition will satisfy, we can just increase our answer and we can say that this is the fully connected component. Fine. So somehow we have to quote this concept. So okay, let us move to the coding part. So this is the IDE. Let us take the graph. We have to convert this thing into this thing because they are giving this edges vector right this, and we have to convert it into graph vector. So let us make the graph vector here. Vector of vector graph, and the size will be v plus 1 because they are using one based indexing and vector int, and then for int I is equal to 0, that will be going up to edges dot size and I plus plus, sorry, and we have to include the adjacent nodes here. So graph of edges I0 we post back to edges I1, and we have to do the rebusting also. I1 dot push back edges I0, right? So now we have converted this information into this, and let us make the answer variable that will be initialized by 0 and the visited array. Okay, and the size of the visited array will be v plus 1, and initially all the values will be 0. Fine. So now let us make another for loop that will be started from 1 and it will go until v and I plus plus. Now check if the current node is visited or not. Then we can, if it is not visited, only then we can call the DFS function. And we have to pass several parameters, like one is graph obviously, then visited, and then the count of node and the count of edges. We can think the out degree also and the current position node. So let us declare int node will be 0 and edges will be 0. Fine. So after that, we can have the sum of nodes and edges. And let us use the formula. If node into node minus 1, if it is equal to edges, then we can say that we have checked a fully component graph. So that is answer plus plus. And at the end, we can return the answer. Now let us write the DFS function. DFS, it takes vector, vector in graph, and we have to pass it by reference. It will save the memory, and vector in, that is what, zted, and we have to pass node and edge, and then ITX, the current node. So this is the time to sum up all the node, that will be plus plus for the current node, and the adjacent nodes that are basically is equal to graph idx dot size, that will indicate the number of adjacent nodes. So now we can visit this current node. Idx will be 1 for int I is equal to 0, I less than what? That is graph idx dot size, sorry, plus plus, and we have to check if the adjacent node is visited or not. If it is not visited, then we can go further. That is graph idx and I. If it is not visited, we can call the DFS function again for the next node. That is uh, graph, visited node, edge, and the current adjacent node. That is graph, IDX, and I. So fine, we have completed our DFS function and we have counted all the fully connected components. So let us try to run our code. Okay, it is showing correctly. Let us try to submit it. Fine. This is working fine. So this is how we can write the code and this is the approach. Now let us talk about the time and space complexity. Time complexity will be big O of V plus E because we are using DFS, and for space complexity that will be the maximum size of the component that will be used in the recursion. Like for this graph, the maximum size is 3. Also, this is also 3, but the maximum size will be 3 here, and the space will be taken that is 3. And also, we are taking this additional graph. So, the additional graph will be the maximum size is, suppose this is a completely fully connected graph. So for each node, we have to store all the other nodes, means the total space will be n into n minus 1. So yeah, that is the space complexity that this approach takes. So hopefully you have understood everything clearly. So thank you for watching and see you in the next video. Bye.